Thanks for watching, and let's do a little bit of practice with the spherical Laplace equation. In particular, let's find all radial solutions of uxx plus uyy plus uzz equals 1, but with the requirement that u is 0 on the sphere of radius 1 and u is 0 on the sphere of radius 6. And for this, let me remind you what Laplace's equation looks like in spherical coordinates. So, step 1, recall. So, in spherical coordinates, Laplace becomes the following, namely uxx plus uyy plus uzz, I believe is urr plus 2 over r ur plus some junk, where the junk depends only on angular derivatives. Now, this, by the way, this is something, of course, it will be given to you if I ask that question. Now, in particular, the cool thing is, if you look for radial solutions, so solutions only depending on r, then all the angular derivatives are 0, and in particular, that junk term then becomes 0. So, upshot, if you're looking for radial solutions, then, namely u equals ur, then junk is 0, and so we get uxx plus uyy plus uzz is just urr plus 2 over r ur. And in particular then, remember our equation was this equals 1, and in particular our equation becomes the following, and so our PDE becomes urr plus 2 over r ur, and remember the right hand side was still 1. Which in this case really becomes just an ODE, because urr in this case is the second derivative of u with respect to r plus 2 over r u prime of r equals 1. Because remember, u here is a function of one variable, which is r. Now, the amazing fact is, even though this is a second order ODE, we can still solve it using integrating factors, which we'll do now. So once again, what was our ODE? It was u double prime of r plus 2 over r u prime of r equals 1. And once again, solve using integrating factors. So in this case, e of integral of 2 over r dr, that is e of 2 times ln of r. So r is a radius, so it's positive. And in particular, the absolute value disappears. And this is e of ln of r to the second power, which is just r squared. Meaning, we just have to multiply our ODE in this case by r squared. And we end up getting r squared times u double prime of r plus 2 over r u prime of r equals 1 times r squared. And once again, by the magic of integrating factors, this whole thing becomes a derivative, so it's r squared times u prime of r prime is r squared, which now we can solve this by integrating twice. So once again, our ODE was r squared u prime of r prime equals r squared. So r squared u prime of r is integral of r squared dr, which if you want is 1/3 r cubed plus a constant a. And so dividing by r squared, u prime of r is 1 over r squared times 1/3 r cubed plus a. So u prime of r is 1/3 r plus a over r squared. And now to find u of r, we can integrate once again. So u of r is integral of 1/3 r plus a, if you want r to the minus 2 dr. And if I'm not mistaken, I believe it becomes 1/6 r squared, and then plus a times r to the minus 1 over minus 1, and then plus a constant b. Which, if you want, you can simplify this now just a little bit. And so what we get is u of r is r squared over 6 minus a over r plus b. And the last thing we need to do is plug in the boundary conditions. So I think it's step 3 if I'm not mistaken. So first of all, use the fact that u of 1 is 0, because u is 0 on the sphere of radius 1. So that gives you 1/6 minus a over 1 plus b is 0, which then gives you b is a minus 1/6. And in particular, we have u now just in terms of a, because u of r is r squared over 6 minus a over r plus a minus 1/6. And lastly, we just need to plug in r equals 6, because we know u of 6 is 0. So 6 squared over 6 minus a over 6 plus a minus 1/6 is 0, which now is an equation that allows us to solve for a, because 6 squared over 6 is just 6. And so a minus 1/6 a, that's 5/6 a. And then we get equals to 1/6 minus 6, which is the same thing as minus 35/6. And so in particular, a becomes minus 35 over 5, which is minus 7. And in particular, we found a, and now we can just plug into this formula. And so let me remind you what we got. We have u of r is r squared over 6, and I believe minus a over r, and then plus a minus 1/6, where a was minus 7. Minus 7. And now we can finally plug everything in. So u of r was r squared over 6, and then minus 7 over r, and then plus minus 7 minus 1/6. And in particular, u of r now becomes r squared over 6, and then plus 7 over r, and then so minus 42/6 minus 1/6, so minus 43 over 6. Which is kind of a cool function. It's a function that blows up at r equals 0 plus, and it goes down, I believe, and has value 0 at 1, and then probably increases to have value 0 at 6, and then it blows up because of this r squared. So that's kind of a cool function. Now, the cool thing is, if you want, you can check that it solves the ODE, but just as a sanity check, let's see if the boundary conditions are satisfied. So in this case, u of 1 is 1/6 plus 7 minus 43/6. And that becomes, in this case, 43/6 minus 43/6, which is in fact 0. And then u of 6, well, that becomes 36/6, and then minus, plus 7 over 6 minus 43/6. And well, 7 minus 43, that is minus 36. So we do get 6 minus 6, which is 0. So at least the boundary conditions are satisfied, which is some good news. And of course, I forgot to mention, don't forget to write your final answer in terms of x and y. So here, using r is square root of x squared plus y squared plus z squared, we then get u of x, y, z is, I believe, x squared plus y squared plus z squared over 6, and then minus 7 over square root of x squared plus y squared plus z squared. And then I believe minus 43 over 6. That would be the perfect answer in this case. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.